Hello there. My name is Dylan Benu, and we're going to be looking at an algorithm that facilitates bulk data storage and data access. Just going to share my screen here. And let's do a slideshow. All right, so as I said, my name is Dylan Binu, and we're going to be looking into bulk data optimization or storage and data access using a Hadoop-based map reduce algorithm. So first, we're going to look into what a B plus tree is. So in short, a B plus tree is an optimized version of the B tree data structure. And if you don't know what that is, I'm not really going to spend time right now getting into it. Hopefully you could Google it or look into it. But a B tree, in short, it's similar to a binary tree. However, it has much fewer layers, usually two or three, and each parent node has more than two children nodes. So in a binary tree, you have each node has two children nodes, but in a B tree, each node has multiple, but you could look further into it yourself. Um, all right, so a B plus tree now is often used in databases. So it is a B tree, but it's altered for the purpose of storing and accessing data in databases. So the problem that we're going to talk about here, it is the bulk data dilemma. So in the Socialist Republic of Vietnam, data processing and security could not keep up with the rapidly growing economy, and the best solution that they had to store, um, uh, I'm sorry, it looks like I have a typo here. Oh yes, no. The best solution that they had to access and store data was the B plus tree. So Hyung Kong Viet New and Jean Ho He proposed a more efficient way of storing and accessing data. It is a Hadoop-based map reduce algorithm, which optimizes the data insertion and data searching process. So this is how a B plus tree works. A B plus tree has a root node at the very top. It has internal nodes in the middle layer, and finally leaf nodes at the very bottom. Now, it is important to note that all the values are stored in the leaf nodes. The root node is first populated, and a value has two child pointers. So if you can see here, 19 is the root node, and to the right side of it, you have a pointer pointing to the right side of it, and to the left, you have a child pointer pointing to the left. So the internal nodes are then populated with each value as it is inserted. So for example, if you're inserting 5, it looks at 19, it knows that 5 is lesser than 19, so it creates a section here, an internal node, and then 5 gets allotted here. And as more values get allotted, these leaf nodes get formed, and then 5 is assigned to the appropriate leaf node down here. So yes, the way that multiple leaf nodes are created is if the capacity of a node is exceeded, the node splits. So for example, here, the maximum capacity for each node is either 2 or 2 plus 2. So in our example here in the internal nodes, it's just, it only has a size of 2. But down here in the leaf nodes, it's using the full capacity of 2 or 2 plus 2, which is 4 here. Hopefully that makes sense. So now after this, the leaf nodes are then populated. I apologize, it's highlighting the internal nodes, but it should be highlighting the leaf nodes. The leaf nodes are populated, and the pointers within the leaf nodes point to the next value and the previous value. So we should remember that the leaf nodes contain all the values in the B plus tree. So for this bulk data dilemma, I think we have realized that the B plus tree is not good enough because the data being inserted sequentially each time means that it's a very time-consuming process. So what is the solution? So Hadoop is a set of open source utilities that provides a framework for distributed storage and processing. A Hadoop-based parallel B plus tree system is proposed to solve this problem. Now we can look into it a bit more right now. The process works in three phases: data distribution, the B plus tree construction, and B plus tree consolidation. Now you might wonder, B plus tree construction, isn't that what we're doing with the B plus tree? Well, yes, but there are a few more steps. So the MapReduce algorithm is employed only in the data distribution and the B plus tree construction phases, which we will eventually get to. So now let's walk through an example of this algorithm being implemented. So we're going to look at a data set that uses, which is basically a large CSV file, and each line in the CSV file represents a transaction. So it will be in this format, OD and OT, and OD is the time of this transaction, and OT is the rest of the transaction, such as the sender ID and anything else that might be involved. So the OD, the transaction time, acts as a unique identifier in this case because you can't have two transactions that took place exactly at the same time, exactly the same millisecond. So it almost acts like as a primary key. So we first look at the data distribution phase, which is the first phase of this algorithm. So in this phase, an input data set will be split into smaller partitions, and the boundary between the partitions will be determined. So you will have an entire data set. Once you get it into this phase, it's going to be partitioned into smaller pieces and hopefully equivalent pieces. So the MapReduce algorithm uses a certain number of mappers which take sample objects from the data set. So right here, you will see we have a data set. It goes into the mappers. It takes a set of sample objects, and then a single mapper takes a transaction time as its value and comes up with a certain constant as a key. So when the data comes out of the mapper as a primary key, you will have a particular constant that the mapper assigns to the transaction. So you can have you can potentially have multiple transactions with the same key value because we're no longer just talking about transaction time, which is what the input was. We're now talking about a constant that the mapper assigns to the transaction. So you can have a single constant with multiple transactions underneath it. And that output would be sent into the reducer. So the mapper, when it passes the output to the reducer, it sorts the input data into a list K in a particular order. And this is where partition boundaries are created. So if you look down here, it takes this constant and list that is formed, and it comes up with a list K, after which it forms these partition boundaries. And these boundaries are now used. It will be used for the next phase where the B plus trees are going to be constructed. So the overall idea is that you are splitting, you're splitting the large data set into smaller little sets, and then B plus trees are forming using those smaller sets. And ultimately, you will notice that one big B plus tree will be formed using all those smaller B plus trees. So now we look at the B plus tree construction phase, which is right after the data distribution phase. So this is the costliest phase in this process because you're actually constructing B plus trees. So the mappers partition the data set into R groups of partitions, and each partition is handled by a reducer. So in the reducer, a B plus tree is built independently using a bulk loading technique in a bottom-up fashion. So in a bottom-up fashion, the leaf nodes are constructed first, then a root node is designated, and using that root node, you will assign internal nodes, or the internal nodes would get formed. So hopefully you can see that here. In the map phase, it takes the initial data, then you get a partition number and transaction. After that, the partition number and list gets sent into the reduction phase, out of which comes a B plus tree and a root. And as I mentioned earlier, this is the costliest phase. All right, so this is the B plus tree consolidation or combination phase. So that all that happens here is all the mini B plus trees that were formed from the multiple reducers are now going to be formed into one single tree, into one single final B plus tree. So to recap, this basically what is happening is the input data gets split up and sent into multiple mappers. The mappers arrange the data in a certain order and they send it into the reducer. And the reducer creates the multiple B plus trees and sends it out. And after it gets sent out, it will then be turned into a final B plus tree at the very end. I hope that makes sense. So now we have the test cases that we're going to be looking into. So let's look at the testing environment. So obviously you need a testing environment to run test cases. So this is what a Hadoop cluster environment may look like. You have a single master node, which acts as the job tracker, and then multiple slave nodes, which act as task trackers. So this is not very important, but just keep in mind that we have multiple systems that help with the partitioning and processing of the data that we're looking into. All right, so we are now going to look into the performance evaluation of the testing that we just did or that was done. So for the performance evaluation, the data sets were once again CSV files similar to our first example, and it contained this format where OD was the transaction time and OT was all the other transaction information. So the three data sizes that were used for these CSV files were 6 GB, 8 GB, and 10 GB. And you can see the number of transactions that each of those files holds over here. So it is in the hundreds of millions. So this is a very large file, and if you were to use a regular B plus tree for this, it could be a lengthy process. So for more accuracy and testing of outlier cases, we're going to be testing 10% of the input file and also 100% of the input file, just to make sure that the results are congruent for different sizes. So this is the first phase of the MapReduce algorithm Hadoop implementation, the data distribution phase. And as you can see, as the number of reducers were increased, the time taken decreases. So the blue represents using 10% of the input file, and the orange represents sorting and creating 100% of the input file, creating a B plus tree using the 100% of the input file. So as you can see, this is done with a 6 GB file, this is done with the 8 GB file, and this is done with a 10 GB file. So overall, across the board, the larger input size seems to experience the largest effect with this algorithm. So you can tell that as the bulk data that you introduce into a company gets larger, implementing out this algorithm would help exponentially with that influx of data. As you can see, with a smaller input size, the change is not that significant, but there is still change. As you can see, it goes from 69 to 46 for this 10 GB, 66 to 40 for the 8 GB, and so on. So we can already see an improvement in the data distribution phase. For the B plus tree construction phase, you can see that during this phase, we are expected to receive equal partitions, which is why here between the 10% and 100% of the input file, the time taken is still pretty similar. It's not as dramatic as you see in the previous phase. So here you notice the same trend with an increasing number of reducers, which means with a larger number of reducers being implemented to create more mini B plus trees to have it finally consolidate into a single B plus tree, you see that the overall time does decrease. And this is the case with all the varying sizes of files. And you can also notice that this is congruent because this is the smallest file, 6 GB. You'll notice that this is 7.8. Here it's 9.74 for the 8 GB and then 10.45 for the 10 GB. I know that there are some discrepancies where here the 10% takes longer than the 100%. However, I think the more important thing to focus on is the downward trend of the time, which does prove that this algorithm was successful. However, how can we determine that it was successful compared to a regular B plus tree? So that's what we're going to do here. So as the number of reducers increases, the time decreases respectively. As you can see here, we're noticing the same trend. Now, with a traditional B plus tree, this is the time that is taken. So you can see that this is already a significant improvement with just 4 reducers and then all the way up to 32 reducers. It goes from 28.5 to 7.46 seconds, minutes. So that is a significant improvement. The same is the case here with our process. We get 1.13 minutes, and with the traditional way, it's 1.85. Likewise, 4.28 and 6.82. So overall, we can consider this to be a successful algorithm that does work in comparison to the traditional B plus tree methods that a lot of the companies in Vietnam are using or were using at the time of this research. So we can conclude that the Hadoop-based Map Reduce algorithm is a far more efficient way to store and access bulk data than the B plus tree. Hence, that is a good reason for why companies should move on to this process. So here are my citations. This is the research paper that I referenced and used. It is a fabulous research paper, and I can also share my reasoning for selecting this paper. I actually have been an intern with Delta Dental of Michigan for the past 10 months, and I work as an application development intern with them. And I, for the first time, got introduced into the JDBC framework, and I learned how Java code connects to the company's database and how you can access information, store information, delete information, etc. And there is a large amount of data over there. And topics like this are often talked about, which is what sparked my interest. I was curious as to why the B plus tree was the most commonly used algorithm or the commonly used data structure out there, which I also talked about B plus trees with my computer science professor in a research project that I've recently been working on. So yes, this is just a topic that it's fascinating to me. So I hope you learned something from it. I hope it was beneficial. And yes, thank you very much for learning. This citation here is just a YouTube video that I referenced, and it just teaches the basics of B plus trees. But thank you very much. That is my presentation, and I hope you enjoyed it.